So now we got a Lego octopus talking to us. Okay, we've got a normal distribution. And we understand, right, that the center is the mean, half the data is above, half the data is below. But then it turns out that the area under this curve follows what's known as the empirical rule. And so how did we know that the mean height for women in the United States is 63.7? Well, we did some research. Someone out there collected some samples. They followed the proper rules of sampling collection, and they found that that was the mean height of women with a standard deviation of 2.7. And we marked that out on the graph below here, 63.7. We added 2.7 to 63.7. So this distance here was 2.7, and we got 66.4. We added it again. We got another 2.7. We could have added it one more time, and we would have gotten another value here. What is that? 71.8. And then for here, we subtracted it. So 63.7 minus 2.7 is 61, and so on and so forth. This is what the empirical rule more or less looks like. We have created what's called 3 standard deviations above the mean. This is +1 standard deviation. This is +2. This is +3 above the mean. This is -1, -2, -3 below the mean. And the empirical rule tells us that there are some very specific or approximate percentages that lie between these standard deviations. Now, our author kind of asks us to guess our way through it, but I'm just going to get you right there because I don't know what the value is in guessing. It's approximately 68% of the values are within 1 standard deviation of the mean. That means 68% of all women are between the heights of 61 and 66.4 inches tall. This would be 68% of the data. In terms of area, that means that area is roughly 0.68. And then within 2 standard deviations, which is between these two numbers, that is approximately 95% of the data, and then 99.7 are within 3 standard deviations. We then get even more specific with that. And we say, okay, from the mean to 1 standard deviation above, we call that roughly 34%. The mean, 1 standard deviation below, that's roughly 34%. And these percentages are the rough approximations for the distribution of the data based on the empirical rule. So if we tell you that a data set is normally distributed, you know that this is the approximate distribution. All right? It's not exactly this. But it's close. This is based off of theory. So this is always true. Well, our author runs us through an M&M example saying that they're approximately normally distributed, and you can read through this example and look at how we put together this normal distribution. We're going to do one ourselves here on the next page. Well, actually, we're going to use his work. We're saying, hey, if our bag has less than 493 M&Ms, how likely do we think that is? What percentage of the bags have less than this? Well, based on the empirical rule, we're noting that 493 bags are 2 standard deviations below the mean. And we would see that that's 2.35% plus 0.5%. And we would expect, because they're normally distributed, that that's going to be 2.5% of the bags. That's what we would expect. That's not particularly likely, right? That's on the lower end, and you're feeling like you're shortchanged in that realm. And then the next question says, how unusual would it be to get a bag with more than 553 M&Ms, so more than this, or less than 481? Well, notice that more than 553, there's only 0.15% of M&M bags that have more than that. And less than 481, there's really only 0.15% that have less than. So you're looking at 0.3% of the bags. That's really unlikely. Highly unlikely. In fact, a general rule in the stats world is anything less than 5% is unusual. Okay, we need to generate one of these for ourselves. So let me just create one for you. We're going to make up a problem. So let's assume that we have a data set that's normally distributed. And let's say that the mean of the data set is 7 and that the standard deviation is 2. Okay, so I'm just giving you a contextless, zero context data set, but I want you to be able to draw the empirical rule. So what we would do is we would start with our normal curve, and we'd say, all right, the center value here, we know it to be the mean. That's got to be 7. And then we do 1, 2, 3 tick marks above. These are the 3 standard deviations above the mean. And what happens is we add the standard deviation to the mean to get each tick mark. So I did 7 plus 2 is 9. 9 plus 2 is 11. 11 plus 2 is 13. These would be the tick marks above. And then based on the theory, I know that this is 34% of the data. This area is 13.5% of the data. This area is 2.35% of the data. And this area is 0.15% of the data. I would then do 3 equally spaced tick marks below. They should be the same spacing as here, and that spacing is 2. I would now be subtracting the 2 from the 7 to get 5. Subtract again to get 3. Subtract again to get 1. And then the same thing. I can extend these lines vertically, and I know that this should be 34% of the data. This should be 13.5% of the data between these two numbers. This should be 2.35% of the data, and this should be 0.15% of the data. So part of what you're being asked to do is if I hand you a blank graph like this, and you should know these percentages, or it's on your reference sheet, can you fill out the numbers on the x-axis given a mean and a standard deviation from the context? And the answer is you should, right? Put the mean in the middle, add the standard deviation 3 times above, subtract the standard deviation 3 times below, and you've got a nice picture of the empirical rule that describes your data set.